Hello, and welcome back. I'm on kind of a roll. I decided to do day 25, 2021. Obviously, still out of season, but I came up with a cool solution for this, so I thought that I would share it. Day 25 on Advent of Code only has one part, so we're just going to be looking at this one. And basically for day 25, we have a rectangular grid with we have spaces, we have right arrows, and we have down arrows. And essentially, we are going to be moving those arrows according to some rules. So the right arrows always move to the right, while the down arrows always move down or south. Fair enough. And then each step, cucumbers in the east-facing herd attempt to move forward location. Forward one location, and then the sea cucumbers in the south-facing herd attempt to move forward one location. So we're going to be processing the right arrows first, and then we'll be processing the down arrows. And then when it moves forward, every sea cucumber in the herd first simultaneously considers whether there is a sea cucumber in the adjacent location it's facing. And then everyone facing an empty location simultaneously moves into that location. So we can't do, basically when we're evaluating this, we have to do it all at once. We can't do it, we can't do like destructive updates one at a time in place. And essentially what it's saying is that if, for example, if we're evaluating the right arrows, if it has an empty space in front of it, then we move it forward. Otherwise, if it has something in front of it, it stays put. Even in this case, right? So this row right here, we have a right arrow, a space, and then another right arrow. So on our first generation, this right arrow is going to move right one space because it has a space in front of it. But this one isn't going to move anywhere because on the current generation, it has something in front of it blocking it, right? So we evaluate the right arrows, then we come back and we evaluate the down arrows, and that constitutes one iteration, right? And there's some examples here. So after one step, yeah, only the front one moves. Then on the next step, the other ones can move, blah, 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 blah. Oh, and this is important. Sea cucumbers that move off the right edge of the map appear on the left edge. And ones that move off the bottom edge of the map appear on the top. So basically they wrap around, which is kind of a pain to deal with. And then it's basically saying, okay, so we're moving. You know, after 4 steps, it looks like this. We have an example. We have an initial state like this. Oh, and it's saying the sea cucumbers need to stop moving. So the idea is that after some number of iterations, all the sea cucumbers will be blocked and they can't move anymore. So if this is our example, after a bunch of steps, looks like 58 steps to be precise, all of these sea cucumbers are blocked. They can't move anymore. So further iterations won't change the configuration at all. And it says they stop moving after 58 steps. And the question is, on our input, what is the first step on which no sea cucumbers move? Fair enough. Okay, so let's get our input first. So as usual, ingit, and I'm going to be operating on the example that they give us first. So if we do this, we get a bunch of lines, we can mix that, and this is our input, right? And we'll call this P. Now, so when we're looking at, basically we have to figure out a way to do iterations here, right? And we have to look, if we're operating on right arrows first, basically we have to look at each right arrow, determine if there's a space in front, or if it's blocked. And if there's a space in front, then we want to move it to the right. If it's blocked, we want it to stay where it is. And we have to do all of that in a single pass, um, so that we don't, you know, if for example we move this one, we don't want to move this one on the same iteration, right? So the way you do this in an imperative language, and actually the way that I initially solved it in APL, is for each um, for each index into the matrix, you might then say, okay, I'm going to look at the space ahead of me and the space behind me, and given that information, I can determine what the proper what element should be assigned to the matrix at that index. So we could do something like if we do like iota row p, this will give us a matrix with all of the coordinates. And actually, if we're going to be doing coordinate stuff, this will make sense in a second, but we want index origin 0 for this. It's not the default. The default is 1. But so if we do this, we get a bunch of coordinates, and then we could, for example, say like for each one of those, I want to generate a set of coordinates such that I'm looking at the element preceding this index and the element after this index. So let's see, we could do iota 3, neg1 plus. This will give us -1, 0, 1 for each one of the cells. We can table that, add 0, concatenate 0, and that gives us this. And then we could say omega plus rank 1 like so. This adds the current coordinate to all of these. So we're building up, we're building up this list of coordinates to look at preceding and succeeding values. Problem is these negative elements. So remember that our sea cucumbers, they wrap around the board. So we need a way to convert these negative elements and the elements on the right side that exceed the indices of the matrix. We need a way to convert those into values so that they wrap around properly. And we can do that with the modulus function. If we do that rank 1 on the shape of P, then we get this. So you can see where this used to be -1, now it's not 0, 9. And actually, if I split these apart like so, now you can see, so in the top left corner, we start at 0, 0. The succeeding element is 0, 1, but the preceding element is 0, 9. And similarly on the right side, our index is 0, 9. The preceding element is 0, 8, but the succeeding element is 0, 0, so it wraps around. And then given these coordinates, we can index back into P to get our data. And now we can kind of go through and we could look at the middle element and say, okay, if the middle element is a right arrow, like say this cell right here, if the middle element is a right arrow and the right element is a space, then we want a space here because we know that that right arrow is going to move. And similarly, for the one right next to it, we can say if the first element is a right arrow and the middle element is a space, then we know that we're going to want a right arrow because we know that we have an arrow moving into this section, right? So yeah, you could do something like this. And this is sort of initially how I did it, but then I came up with a more elegant, more array-based solution, which I'm going to be showing you. And this solution is predicated on us getting our input in a certain way. So we have P, our input. I'm going to assign this to, let's say, T for text so that we have a picture that we can look at. But right now, we're going to modify this a little bit. So we're going to say, okay, for right arrows and down arrows, I want outer product equals of our input. And this gives us a Boolean rank 3 array, where in the top matrix here, all the ones represent the spaces where the right arrows are. And the bottom matrix here, all the ones represent where all the down arrows are. And we're going to actually, this is our input that we're going to be working with, so I'll assign this back to P. And, you can convert back from this by, let's say, like at 2, we can do multiply by 2. Oh, right. Let's switch back to IO1 just so we're in the default. So we get this, and then we can add them together. Oh, reduce first, like so. And then if we add 1 and we index back into it using space, right arrow, down arrow, we can get a picture like this. And this should match our text input that we saved earlier. So we can convert back from our the format that we're using for our problem input back into some representative picture so we can check our work. Okay, so why did we do this? Basically, the reason why we've separated this into two matrices is it allows us to work on the right arrows and the down arrows independently. At each iteration, we're going to be doing the right arrows first and then the down arrows. So it's helpful to have it separated in this way so that, you're only working on whatever the active piece is at any given time. That could be right arrows, could be down arrows. Okay, so if we're going to be iterating, the first thing that we're going to be looking at is the right arrows, and that's our top matrix here. And if you think about it, we can separate all of the right arrows into two categories. We have right arrows that are going to move, meaning that they have a space in front of them, and we want them to move forward. Or we have right arrows that are staying put. And a right arrow will only stay put if it has some other arrow, could be a right arrow, could be a down arrow, that's blocking it from moving, right? So if we calculate both of those sets and then we put them together, that'll be a complete iteration, right? Okay, let's first calculate the right arrows that are going to move. In other words, we want to find all of the right arrows that have a space directly in front of them. So we can get the first matrix by doing 1 index P, like so. And then we can rotate it. So if we do a neg1 rotate, then we get basically this is shifting all the elements right. So you can see we had a 1 in the upper right corner that's now in the upper left. This 1 in the lower right corner is now in the lower left, etc., etc. Basically, we've just taken all the columns, shifted them right 1, and then the rightmost column has now become the first, which is useful because remember that our sea cucumbers, when they're moving, they wrap around the matrix, right? So we've now moved all of our right sea cucumbers to the right, and we only want to keep the ones here that have a space in front of them. And we can do all of this basically with just Boolean functions. So we can take, well, let's save this for now. But basically, if we do an or reduce first on P, this now has ones in all areas where there's either a down arrow or a right arrow. And if we apply not to this matrix, now we have ones in all the space in all the locations where there's empty space, right? So this says not any location, not any location where there's an up arrow, or sorry, where there's a right arrow or a down arrow, right? So we have that. If we take all of our right arrows that have moved that have rotated right by 1, and we say and there has to be a space in its new location. So we do and not all the locations where there's down arrows or right arrows, right? Oh, and I have to put P here. So this is, if I, hang on one second, I can visualize this. That might be easier. So dot right like so. So these are all of our right arrows that have moved right by 1 location. If we compare this with our problem input, so for example, in our problem input, we would expect this one to move right by 1 space, and there it is. We would expect this one to move right by 1 space, and there it is, right? Same for these 2 right arrows. We would expect them both to shift right by 1, and they have. So you can see that basically we've generated the set of the right arrows that are going to move. As I stated previously, if we take this and combine it with the set of right arrows that don't move, then that's all the arrows. And so that constitutes a complete iteration. So how do we find all the arrows that don't move? Well, again, we can take or reduce first P, right? So we have all the ones here represent they represent either down arrows or right arrows. And then we can rotate it to the left by using a positive number to rotate here. So we've rotated everything to the left now. And you can think that, okay, if I do this and I and 1 index P, what I'm saying is give me all of the right arrows that have some object in front of them, right? So we have this or reduce P represents all objects, whether they're down arrows or right arrows. We rotate it to the left, and then we and it with the locations of our right arrows. And so you can think about if we shift the matrix left, there's some overlap there, and we basically just want to keep all of the right arrows that have some object directly in front of it, like so. And again, I can help visualize this, and I'll have to do 1 plus here. So these are all the arrows that are staying put. And if we look at T, we would expect this arrow to stay put because it has an object directly in front of it, and indeed there it is. This one's staying put because in our input, this right arrow would wrap around and would run into this down arrow here, right? We would expect this right arrow to stay put because it has one directly in front of it, and it does, et cetera, right? Both of these are staying put because they have stuff in front of them. They're both right here. So, right. So this expression here represents all of the arrows that are staying. This expression here represents all of the arrows that are moving. And so what we can do is we can just OR them together to get the set of all of the right arrows, whether they're moving or staying put. So we'll just put parentheses around this, and then OR this, right? This is all of our arrows. Let's visualize it. 1 plus. So all of our right arrows are here. We have these two. This one stayed put. This one moved forward, so that looks correct. This one stays put. These 3 are like this, and that seems correct because this first one would stay put, and then the latter 2 would move right by 1, et cetera, right? So basically, we can do all of this checking simply using rotation and Boolean functions. ands and ors. And there's a not there too. Okay, well, and then because of the way that our problem input is structured, you know, we could say, you know, we concatenate this with the one drop of P, and this will give us a new problem input, but with the right arrows all calculated for the next iteration. But how are we going to do the down arrows? Well, if we look at our text input here, let's think about what the down arrows do. So the down arrows are operating along the columns here. They're trying to move down. And just like with the right arrows, if there's a space in front, then they want to move down. And if they're blocked, then they stay where they are. So the logic is exactly the same as it is for the right arrows. The only difference is that we're operating on columns rather than rows. So if we could transform our data somehow so that we can swap the rows and the columns, then we could use the same logic. And then if we swap the rows and columns again, we'll be back to our initial configuration and ready to do the next iteration, right? So for down arrows, it follows the exact same logic as it does for right arrows. We're just operating on columns rather than rows. So luckily, there is a way to do that, and it's just transpose, basically. So what we want to do is we have a rank 3 array here, and we want to transpose the two matrices inside of that, and we can do that with dyadic transpose, like so. Dyadic transpose is kind of confusing. It took me a long time to understand it. But basically, you can think of the left argument as just telling which axes you want to reorganize, right? So in this case, we're moving the third axis to the middle and the second axis to the end here in terms of the shape. Okay, but the problem is that our logic is operating on the top portion of the matrix. Well, actually, hang on. First, let's make this into a function so that we can actually use it to iterate. Now I'm looking at this, and I could make it a function using the squiggly brackets and the omega, but just looking at it, this can be made into a train. And so we can say instead of one index p, we can do one jot, like so. This we don't need to specify p because it will just operate on the input. Same here. And then here we can also do one jot like so. And then let's get rid of this portion for the moment. Let's call this f. So if we run f on p, this is our newly calculated right arrows. Or in other words, we ran the calculation on the top matrix of our input. And then we can concatenate that with one drop like so. And what this is doing is this is taking our newly calculated matrix and it's moving it to the bottom. And then it retrieves the bottom matrix from our input and moves it to the top. So that when we do another iteration, we're going to be this top matrix is sort of our active matrix that we're doing calculations on, right? And then we can transpose it using dyadic transpose like we showed before. And if we do this, now everything's switched around. The rows have become columns, columns have become rows, and our matrix representing the down arrows is now on top. And we can apply the exact same logic. So if that's our complete function, then if we run it twice on P, this is one complete iteration where we've calculated the new locations for the right arrows and the down arrows. So if we visualize this at 2, 2 times plus reduce 1 plus dot like so. So this is what it looks like after we've done one complete iteration. And if we look at our example input, we can compare it to the after one step here. Right, and this looks the same. So we can see that our calculation functions appear to be working correctly because it matches what happens, what the sample input looks like after a single step. Now, what the question actually asks is, it says, how many steps does it take before the sea cucumbers all stop moving? And if we want it to stop moving, then we can use power match here, just like I did in my last video, where basically we keep running this function. Well, we have to run the function twice, and then we have to keep running it until we achieve convergence. So each time that we run it, we're going to run this function twice to calculate the right arrows and the down arrows. And then we'll keep running that until the values don't change anymore. And if we do that, we get this configuration, which looks correct. It looks like all the sea cucumbers are blocked. And if we copy the final configuration here, like so, this again looks the same. So it looks like our calculation function is running fine, and we can find the sort of terminal state where nothing changes anymore. Now the problem is we need to figure out how many iterations it takes. APL doesn't really have a great way to do that, so what you do is you initialize some counter, and then you can say we're going to run the function twice on the input, but before we do that, we're going to increase our counter, and we run that until convergence on P, and we get 58. So it took 58 iterations, and that's how much it takes for the sample input, right? Okay, so let's put together our solution in the text editor here, and then we can run it on our actual input. So what was it? First, we need to get our input. Scrolling. There was a lot of a lot of stuff here. Okay, yeah. So it's just P. Write down outer product equals mix take inget 25.txt is our actual input. And then we specified our transition function down here somewhere. This is F. And then this is our actual calculation, like so. Part 1. Okay, so if we change our input to the actual, if we use the actual input rather than the test input, the size of this is quite large. So it's a 137 by 139 matrix as our input, but we have this leading 2 because we separated out the right arrows and the down arrows. But if we run our calculation on the actual input, we get 321, and that is indeed our number. Now the interesting thing about this is that first solution that I was showing you with where you generate all the indices and you're sort of doing modulo to make sure that it wraps around and you're checking the preceding and succeeding elements. The solution that I came up with for that took like 30 seconds to come up with the final answer. This is obviously much faster. The question is how much faster? So if we pull comp x from defins, and then we say, we could just calculate the final state here for p. How long does it take? And the answer is like 13 milliseconds. So this is obviously much faster because we're not, there's no each in here. We're not operating on any cells individually. Everything here is operating on large arrays. And there's no conditionals or anything, so we're not, we don't have any cache misses in the processor or anything like that. So for APL, I mean, it's not Rust or anything, but this is quite fast for this problem. But yeah, this is our complete solution in 3 lines. And I thought it was cool because we're basically just doing a bunch of Boolean operations here. We're able to reuse the logic by applying transpose rather than having separate rules for our right arrows and down arrows. And then who doesn't love a good power match combo here? I always think those are fun. So yeah, that's day 25. Again, there's only one part for the day 25 problems. And that is it for this video. Yeah, as I said in my previous one, I'm not sure that I'll be making any more. But who knows? I'm kind of going through these, and this is sort of piquing my interest at the moment, so there may be more. Anywho, until next time, thanks for watching.